Welcome back to ByteLearn. In the last episode, we ended with a problem. Naive modulo hashing breaks completely the moment you add or remove a database shard. 75% of all your keys route to the wrong location. In production, that means hours of incorrect reads and writes during migration. This episode is the solution. Consistent hashing limits that remapping to just 1 over n of your keys, regardless of cluster size. This is the algorithm that powers DynamoDB Cassandra, Redis Cluster, and Memcached. By the end of this video, you will understand exactly how it works and how to use it in a system design interview. The number to remember is 1 over n. If you have n servers and you add or remove one, consistent hashing guarantees that only 1 over n of all keys need to move, the theoretical minimum. With 4 servers adding a fifth remaps exactly 20% of keys. The other 80% stay exactly where they are. No migration, no downtime, no cache invalidation storm. Naive hashing remaps 75%. That difference is why consistent hashing exists. Every major distributed data system you will encounter in a system design interview uses consistent hashing or a direct variant of it. DynamoDB handles over 10 trillion requests per year using a ring-based consistent hashing scheme with virtual nodes. Cassandra uses 256 virtual nodes per physical server. Redis Cluster uses 16,384 hash slots, a pre-sharded variant of the same idea. If you are designing a distributed cache, a sharded database, or any system where data lives across multiple nodes, consistent hashing is the answer. We start with a quick recap of why modulo hashing fails at scale. You saw this at the end of episode 5. Then we build the consistent hashing ring from scratch. Hash space, server placement, key routing. We trace what happens when you add or remove a server and prove the 1 over n remapping guarantee. We cover virtual nodes, the technique that fixes uneven distribution in large clusters. We walk through failure handling and replication. And we finish with the 4 question framework that answers any consistent hashing question in a system design interview. This video is for two audiences. If you are a backend engineer working on systems at scale, whether that is a Redis cluster for session management, a Cassandra cluster for time series data, or a distributed database for user records, this video shows you exactly what is happening inside those systems when topology changes. And if you are preparing for system design interviews at companies like Google, Flipkart, Amazon, or Swiggy, consistent hashing comes up in almost every distributed systems question. This video gives you the full answer, not just the keyword. Stay till the end. We are going to show you why virtual nodes are the critical addition that makes consistent hashing usable in production. Without virtual nodes, consistent hashing is theoretically elegant but practically broken. One server might own 40% of the ring while another owns 5%. Virtual nodes fix that, and we will show you how Cassandra's implementation works in practice, taking data from every existing node simultaneously when a new server joins. That is the production grade version. One prerequisite. Episode 5 on hashing simplified is the direct setup for this video. We pick up exactly where that episode ended. The failure mode of naive modulo hashing. If you have not watched it, the link is in the description. Everything else in this video we build from first principles starting now. Quick recap from episode 5. Modulo hashing, hash of key modulo n, is perfect when n never changes. Deterministic O of one routing, no external directory needed. The problem is the word never, the moment you add a server. Because traffic grew or you need more capacity, the routing rule changes from modulo n to modulo n plus 1. For most keys, those two computations give different results. The data is on one shard, the query goes to another. In a live production system, that is a disaster. Consistent hashing replaces modulo arithmetic with a geometric idea. Instead of dividing by n, we arrange the entire hash space 0 to 2 to the power of 32, about 4 billion values, into a circle. Servers are placed on this circle by hashing their own names. Keys are routed to the nearest server in the clockwise direction. When you add a server, it claims only the segment between itself and its predecessor. When you remove a server, its segment passes to the next clockwise neighbor. In both cases, only the directly affected segment remaps. Everything else is untouched. 3. Production variants of consistent hashing. The classic ring, used by DynamoDB and Cassandra, maps servers to positions on a 2 to the 32 circle with virtual nodes. Redis Cluster uses a pre-partition variant, 16,384 hash slots, each assigned to a node, with the slot table broadcast to all clients via the cluster bus. Ketama, the original Memcached implementation, uses a sorted array of node positions, functionally equivalent to the ring. All three variants solved the same problem. Let us build the ring from scratch. Start with the simplest case, one database node handling all traffic. Every read and every write from every user lands on this one machine. For early stage products, a few thousand users, modest data size. This is fine. It is simple to operate, easy to back up, and trivially consistent. The problem appears when it stops being enough. Vertical scaling, adding more CPU and RAM to the same machine, has a hard ceiling. The largest cloud database instances today have around 96 virtual CPUs and 768 gigabytes of RAM. At Flipkart's big billion day scale, 150 million users in a 24-hour window, even the largest single instance cannot keep up. And beyond cost, single node databases have a write throughput ceiling: one disk, one write ahead log, one lock manager. Adding CPUs does not help if the bottleneck is I/O. The solution is horizontal scaling, splitting the data across multiple machines called shards. Each shard owns a subset of the key space. 3 shards means each machine handles roughly one-third of all reads and writes. Adding a fourth shard reduces load further. The total capacity of the cluster scales linearly with the number of nodes, not with the size of any individual machine. With sharding, every request passes through a router that decides which shard owns that key. User 1001 hashes to shard A. Always. The routing is deterministic, so every future request for user 1001 also goes to shard A. All of that user's data stays co-located. No cross-shard joins needed. User 2002 hashes to shard B. Each user is pinned to exactly one shard. Let us trace one more. User 3003 hashes to shard C. 3 users, 3 shards, 3 deterministic routes. The routing computation is O of 1, no directory lookup, no coordination needed between shards. This is the correct foundation. The question is, what routing rule gives us this determinism without breaking when n changes? Start with 3 shards, A, B, and C, and modulo 3 routing. For any user ID, compute the hash. Take modulo 3 and the result 0, 1 or 2 determines the shard. User 1001 hashes to shard A, user 2002 hashes to shard B, user 3003 hashes to shard C. This has been working perfectly for months. Now the database is growing, you need to add a fourth shard. With 3 shards, routing is correct. Hash of 1001, modulo 3 is 1. Shard A user 1001's data is on shard A. The query reaches shard A. The data is there. Everything works. Shard D is added. The cluster now has 4 nodes. The routing rule must update from modulo 3 to modulo 4. This seems like a small change. One extra shard, one extra modulo value. The consequences are enormous. For most values, hash modulo 3 and hash modulo 4 produce different results. Specifically, about 75% of all keys, 3 out of every 4, now map to a different shard than they did before. User 1001 might now map to shard C instead of shard A. User 2002 might now map to shard D. Their data is still on the old shards. The queries are going to the new shards. Every one of those queries returns wrong or missing data. To fix this, you must migrate data, moving 75% of all records from their current shard to their new shard while the system is live and serving traffic. This is a multi-hour operation involving every shard simultaneously. During migration, reads may return stale data, writes may go to the wrong shard. This is a production incident, not a routine scaling operation. The fundamental problem is that modular hashing makes shard assignment globally dependent on n. Change n anywhere and everything changes everywhere. Consistent hashing fixes this by making shard assignment depend only on a local segment of the ring. Consistent hashing starts with the hash space, all integers from 0 to 2 to the power of 32, approximately 4 billion values. Instead of treating this as a linear number line, we bend it into a circle. 0 and 4 billion are adjacent. This circle is called the hash ring. Each server is placed on the ring by hashing its own identifier, typically host name or IP address. Server A hashes to position 80, server B hashes to position 160, server C hashes to position 240. These positions are fixed. They do not change as long as the server's name does not change. The servers are scattered across the ring based on their hash values. To route a key, compute its hash, which gives a position on the ring. Then walk clockwise from that position until you hit the first server. That server owns the key. Key with hash 105 walks clockwise from 105, hits server B at 161st. Server B is the owner. Key with hash 195 hits server C at 240. Key with hash 50 hits server A at 80. This is the entire routing algorithm. One hash computation, one binary search on a sorted list of server positions. O of log n. To add server D at position 120 between A at 80 and B at 160. Server D now claims the segment from 81 to 120, keys in that range used to route to server B. Now they route to server D, keys in every other segment, 121 to 160, 160, 161 to 240, 241 to 80 are completely unaffected. The fraction of keys that remap is exactly 1 over n, with 4 servers adding a fifth remaps 20%. With 100 servers, adding one more remaps 1%. To remove server A, its segment 241 to 80 passes to server B, the next clockwise node. Every key that was on server A now routes to server B. Keys on every other shard are untouched. If server A failed, server B absorbs its load automatically as soon as the health check detects the failure. The ring reorganizes without touching any other segment. This is why consistent hashing is the foundation of every high availability distributed data system. The mathematical guarantee for k total keys and n servers, adding or removing one server causes exactly k over n keys to remap. The theoretical minimum. You cannot do better than this. Any algorithm that remaps fewer keys would have to put some keys on the wrong server. Consistent hashing achieves the theoretical optimum. This is provable with a simple argument. Each server owns 1 over n of the ring on average, so adding one server claims 1 over n of the total key space from its predecessor. 3 servers on the ring. Server A at position 80, this is hash of server A's hostname, mapped to a position between 0 and 4 billion, then scaled to 0 to 360 for the diagram. Server B at position 160, server C at position 240. The ring router knows these positions, either from a configuration service or from a gossip protocol between nodes. Key session colon 1001. The router computes murmur hash of the key string, producing position 105 on the ring. Walk clockwise from 105. The first server encountered is server B at position 160. Server B owns this key. Session 1001 routes to server B. Every future request for this session key will also compute hash 105 and walk to server B. The routing is deterministic. Same key, same server every time. Second key, user 2002. Hash of this key is 195. Walk clockwise from 195. Next server is server C at 240. Server C owns this key. User 2002 routes to server C, server B, which owns 81 to 160, is skipped. Position 195 is past server B's 160, so it wraps to server C. Third key, order 3003. Hash is 50. Walk clockwise from 50. The first server is server A at position 80. Server A owns this key. Order 3003 routes to server A. Notice that server A's segment wraps around the ring. It owns keys from 241 past 0 to 80. Position 50 is in that wrapping segment. So server A is the owner. The ring data structure handles this wraparound naturally. All three requests return data correctly. Server A returns order 3003. Server B returns session 1001. Server C returns user 2002. The routing cost is O of log n, a binary search on the sorted list of server positions. For 100 servers, that is 7 comparisons. For 1000 servers, 10 comparisons. The ring scales efficiently even as the cluster grows large. Starting state, 3 servers on the ring. Server A at 80, server B at 160, server C at 240. Routing is working correctly. Now we need more capacity and add a fourth server. Server D at ring position 120. Server D is provisioned and joins the ring at position 120. This position is between server A at 80 and server B at 160. Server D claims the segment from 81 to 120, the range between its predecessor A and itself. The only affected segment is 81 to 120. These keys previously routed to server B because server B was the first clockwise server from those positions. Now server D sits between them and server B, so those keys now route to server D. The data must be migrated from server B to server D for this segment only. Every other segment is untouched. The router updates its ring state, inserting server D at position 120. Immediately, all keys in the 81 to 120 range route to server D, with 4 servers equally spaced on the ring. Each server owns approximately 25% of the key space. Adding a fifth server remaps 20%. The fraction that remaps is always 1 over n, regardless of how many servers you have, regardless of cluster size. User 1001 with hash value 50 still routes to server A at position 80, unchanged. User 2002 with hash 1095 still routes to server C, unchanged. Only the 8% of keys in the 81 to 1000 segment saw any change. The other 92% of traffic continues with zero disruption. No cache invalidation storm, no incorrect database reads. This is the operational advantage of consistent hashing. Same operation adding a fourth server, modulo hashing 75% of keys remap. Consistent hashing 8% remap. That 67-point difference is the operational gap between a production incident and a routine scaling event. This is why consistent hashing was worth inventing and why it is now the default algorithm in every distributed data system. Without virtual nodes, servers are placed at their hash positions, which are random. In a small cluster, random placement almost never produces even distribution. One server might land near 2 others and own a tiny slice. Another might own nearly half the ring. With 256 virtual positions per physical server, the law of large numbers kicks in. Each server ends up owning approximately 1 over n of the total key space, regardless of its hash values. When a server fails, without virtual nodes, all its keys go to one neighbor, potentially doubling that neighbor's load. This creates cascading failures. With virtual nodes, the failed server's 256 virtual positions are scattered across the ring. When they go dark, their load distributes across all remaining n-1 servers. Each absorbs only a small fraction, no single server spikes. Adding a server without virtual nodes takes one contiguous block from one neighbor. With virtual nodes, the new server's 256 virtual positions are distributed across the ring, taking small fractions from every existing server simultaneously. The new server reaches its target load immediately without needing any server-to-server coordination. Cassandra calls this automatic token assignment. Hot partitions are a major operational risk in distributed databases. If your keys are sequential like timestamps or auto-increment IDs, they may cluster near one server's ring segment, creating a hot partition. With virtual nodes, the hash function's output is scattered across 256 positions per server. Sequential input keys land on different servers, breaking up the clustering. The trade-off: Virtual nodes add operational complexity. Debugging a routing decision requires understanding which virtual node a key maps to. Cluster management is more involved. In practice, Cassandra, DynamoDB, and Redis Cluster all have tooling that handles this automatically. For clusters larger than 5 nodes, the distribution benefits of virtual nodes far outweigh the operational overhead. In a production consistent hashing cluster, data is replicated across multiple nodes, not just the primary owner. Cassandra, DynamoDB, and most production systems use a replication factor of 3. Each key is stored on the primary node and on the next two clockwise neighbors. This means losing any one server loses no data as long as the other two replicas are healthy. Normal operation: user 1001 routes to server A as the primary. Reads go to the primary, writes go to the primary, and replicate to the next two clockwise nodes, server B and server C, before acknowledging success, depending on the write consistency level configured. Server A fails, hardware fault, network partition, or process crash. The ring router detects the failure through health checks. In Cassandra, each node sends heartbeat signals via a gossip protocol every second. Missing 3 consecutive heartbeats about 3 seconds triggers failure detection. The router marks server A as down and updates the ring. The ring updates. Server A's segment, the range it owned, now routes to server B, the next clockwise neighbor, because server B already holds a replica of all of server A's data. Replication factor 3. Server B can serve those reads immediately with no data migration needed. The failure recovery is instantaneous from the client's perspective. The next request for user 1001 routes to server B, which now owns server A segment and already has a replica of the data. The client receives its response. From the client's perspective, one request timed out and the retry succeeded. The failure was transparent. Response returned from server B's replica. No data lost. Replication factor 3 means the system can tolerate any two simultaneous failures without data loss. This is why Cassandra, DynamoDB, and similar systems require a minimum replication factor of 3 for any production deployment. When server A recovers and rejoins the ring, it retakes its original segment. During its outage, writes intended for server A were stored on server B and server C as hinted handoffs, temporary write records, noting that these writes must be replayed to server A when it returns. On recovery, server A replays all missed writes, verifies consistency with its neighbors, and resumes as a normal ring member. The ring returns to its original state without any manual intervention. DynamoDB, Amazon's managed NoSQL database, uses consistent hashing with virtual nodes as its core partitioning algorithm. Each DynamoDB table is partitioned across many physical servers. Virtual nodes ensure even distribution. Partition keys are hashed using murmur hash to determine which partition and therefore which physical server owns each item. DynamoDB handles over 10 trillion requests per year on this foundation. When a table partition splits due to hot traffic, DynamoDB adds virtual nodes automatically. Consistent hashing makes this operationally safe. Cassandra is the most explicit consistent hashing implementation in widespread use. Each physical server gets 256 virtual nodes called tokens distributed across the ring. The ring state is shared via a gossip protocol. Every second, each node exchanges ring state with 3 random peers. Within seconds, all nodes have a consistent view of the ring. Replication factor, the number of consecutive clockwise nodes that hold each key, is configurable per table. Instagram uses Cassandra at over a billion rows per table on this architecture. Redis Cluster uses a variant called hash slot sharding. The key space is divided into exactly 16,384 slots. Each key maps to a slot by hash of key modulo 16,384. Each node owns a subset of slots. The slot to node mapping is broadcast to all cluster participants via the cluster bus, a separate TCP connection on port 16379. When a node is added or removed, slots are reassigned without remapping the key space computation. Swiggy, Flipkart, and PhonePe use Redis Cluster for session management and real-time rate, limiting at millions of requests per second. Ketama, developed at last at FM and popularized by Facebook, is the original consistent hashing implementation for Memcached. It uses a sorted array of server positions and binary search for routing, O of log n. Facebook used Ketama to manage pools of over 100 Memcached nodes, routing hundreds of millions of requests per minute. When they needed to add cache nodes during traffic spikes or infrastructure expansion, Ketama guaranteed that only 1 over n of cache entries went cold. The rest remained warm. Every major Indian internet platform at scale uses consistent hashing for session and cache management. IRCTC's login sessions are stored in Redis. Consistent hashing ensures that adding Redis nodes during tactical booking spikes does not invalidate millions of active sessions. Swiggy's order state is cached in Redis cluster. Adding nodes during peak dinner hours remaps only 1 over n of cached orders. Ola's driver location data, sharded across Redis nodes by geohash, can be rebalanced without dropping location updates. Consistent hashing is not academic, it is the operational foundation of every Indian super app. First question: can the number of nodes change? If your system needs to scale out or tolerate node failures, n will change. Use consistent hashing. If you are building a small fixed size system where the number of nodes is truly constant, a local cache with exactly 3 nodes forever, modulo hashing is simpler and correct. In practice, almost every production distributed system expects n to change. Default to consistent hashing. Second question: how many replicas? Replication factor 1 means any single node failure loses data. Replication factor 2 means a simultaneous 2-node failure loses data. For any production system, the minimum replication factor is 3. Pair this with quorum writes, requiring at least 2 of 3 replicas to acknowledge a write before confirming success. This gives you durability without sacrificing too much write latency. Third question: will you use virtual nodes? For any cluster larger than 5 nodes, the answer should be yes. Without virtual nodes, uneven ring distribution is nearly guaranteed in small clusters and becomes a hot partition risk in large ones. The standard is 150 to 56 virtual nodes per physical server. Cassandra defaults to 256. Mention virtual nodes explicitly in any interview answer about consistent hashing. It shows you understand the difference between the theoretical algorithm and the production-ready implementation. Fourth question: are any individual keys intrinsically hot? Virtual nodes solve uneven distribution across the key space. They do not solve the case where a single key receives disproportionate traffic, a celebrity user's profile, a trending product, a viral post. For these cases, you need application level mitigations, cell-based sharding where one key is deliberately split across multiple cells, or read replicas with request fan-out. Consistent hashing routes celebrity keys to one shard, and that shard can become a hot partition regardless of how good your ring distribution is. The answer structure that distinguishes you in any distributed systems interview. Start: can n change? Yes. Use consistent hashing with virtual nodes. State replication factor 3 with quorum writes for durability. Mention how adding a node remaps only 1 over n of keys. Show you understand the guarantee. Acknowledge the hotkey limitation and offer a mitigation. End by naming the production system that matches: DynamoDB for managed, Cassandra for self-hosted, Redis Cluster for cache. 4 components, 1 complete answer. Before consistent hashing was formalized in the Dynamo paper in 2007, distributed databases treated shard count as a fixed parameter. Changing it required scheduled downtime, manual data migration, and careful coordination across every database node. The operational cost was so high that many teams simply never rescaled. They vertically scaled individual nodes until they hit the ceiling. Consistent hashing made horizontal scaling operationally safe. It changed distributed databases from fixed topology systems into elastic ones. The 2007 Amazon Dynamo paper, Dynamo, Amazon's highly available key value store, is the most influential systems paper of the last 2 decades. It formalized consistent hashing with virtual nodes, quorum-based replication, and gossip-based ring state management. Every distributed database built after 2007, Cassandra, React, CouchDB, ScyllaDB, references Dynamo as its architectural blueprint. If you read one systems paper before a distributed systems interview, make it Dynamo. The link is in the description. Consistent hashing is not abstract theory for Indian internet companies. It is the reason their platforms survive peak traffic events. Flipkart can add Redis nodes live during big billion days without invalidating millions of active shopping sessions. IRCTC can scale its session cache during tactical booking without logging out every user. Swiggy can extend its order cache tier without dropping a single live order update. PhonePe can grow its transaction cache without corrupting idempotency records. In every case, consistent hashing provides the guarantee: add a node, only 1 over n sessions, orders, or transactions move. The rest stay exactly where they are. Consistent hashing is one of those ideas that is simple enough to explain in one sentence. Hash the key, walk the ring, take the first server you hit, yet deep enough to power the world's largest distributed databases at trillion request scale. One algorithm: virtual nodes for distribution, replication for durability, gossip for ring state. This combination is the foundation of elastic distributed infrastructure. You now understand it completely. That is consistent hashing, from the failure of modulo hashing through the ring structure, the 1 over n remapping guarantee, virtual nodes, failure handling, and the production implementations in DynamoDB, Cassandra, and Redis Cluster. You now understand not just the algorithm, but why it was invented, how it is deployed at scale, and what it enables for distributed systems at Indian internet scale. Here is what you can now do. Explain precisely why modulo hashing fails when n changes, and quantify the damage at 75% remapping. Draw the consistent hashing ring on a whiteboard and trace key routing step by step. State the 1 over n remapping guarantee and explain why it is optimal. Design a production-grade consistent hashing cluster with virtual nodes, replication factor 3, and gossip-based ring state, and name the production system that matches any given scenario: DynamoDB, Cassandra, or Redis Cluster. Next video, the CAP theorem. You just built a mental model of how distributed data systems handle scaling and failure. The CAP theorem is the fundamental constraint. Those systems operate under consistency, availability, and partition tolerance, and you can only guarantee 2 of the 3 simultaneously. Episode 7 shows you why that trade-off is unavoidable, how Cassandra and DynamoDB sit on different sides of it, and how to reason about CAP in a system design interview. Link in the description. Subscribe to ByteLearn for one system design concept per week, explained through animated diagrams, grounded in real production systems, and interview ready. Hit the bell. CAP theorem drops next Wednesday. One question before you go. Which production system using consistent hashing surprised you most? That DynamoDB's 10 trillion requests per year run on a ring structure, that Cassandra assigns 256 virtual positions per physical server, that adding a single Redis cluster node remaps only 1 in n keys while leaving the rest untouched, or that IRCTC's statical session cache relies on consistent hashing to stay alive during booking spikes. Drop it in the comments. It tells me which examples land best for the next video.